So, yeah. So in the final exam, you are allowed to prepare one. Okay, either you want open book or you want one formula sheet ready with you. But last time it used to be open book, but I think I'll restrict you to only one foresight formula sheet in the midterm exam. Okay, so you can copy down whatever formula. Okay, take for example, you can copy down this dim element formula. Okay, but the important thing is still how do you do the solution. Okay, take for example here. Just now we have to identify what is fixed. Okay, the fixed one will be associated with reaction force and reaction moment. And what is free? Free one have the displacement to be determined. They could be loaded or they could be not loaded. Okay? But when you read the solution, you only look at the free notes, free displacement, because you're going to solve them. So as a result, you can reduce to this equation. Okay? If the equation is 2 by 2, okay, then you can do the Kramers rule for the solution. If the equations are 3 equations, there are three simultaneous equations, then what you have to do is by Gaussian eliminations. First, look at this simple example. How do you do Gaussian elimination for these 2 simultaneous equations? The whole purpose is to triangulize the coefficient in the matrix. Okay? So you have to zero out the left corner. Okay? So you can do so by doing some operation between the row. Let's take the second row plus half the first row of the equations. Then you manage to zero them out. Okay? As a result of zeroing them out, then you can go back to do the solutions. Okay? Upon finding the variable for the last row, okay, you got the theta 2, then you substitute them back to the previous row. Okay? So if you're not sure about Gaussian elimination, please go back and study that or practice it. Okay? So, yeah, in the last example, we managed to solve this for the vertical displacement at the free end and the rotation at the free end. Okay. So this is a simple validation. It's validated to match with the theory. Okay, beam bending theory. And then next, so the next question, what we're going to do is, okay, for a beam structure which has more than one beam, okay, then you could have 2 beams look like a bridge support, but left hand clamp, right hand beam support, and the middle node subjected to moment, and then the tube load. How do you solve for that? Yeah. First, write the first equation. Okay. Identify the 3 nodes. Next, write the second equation for the second element's force balance, and then identify the 3 nodes. Because the second element has 1 pin support or not 3, the pin support will not restrict the angle of diffraction, okay, but only restrict the vertical displacement. So that's why you have the first row, second row, and the fourth row of equations all being, all having non-zero displacement and the corresponding variable. Okay, so in that way, you got the 3 by 3. You got 3 equations or 3 forces to be summed up. So in summary, for first element, you got 2 equations. For second element, you got 3 force equations. Let's do the summing. How to do the summing? Okay? To do the summing, you are really doing the summing of the force. look at the variable, okay, then look at the one correspondent, okay, then you add up the force together. So only this corner, you have the force contribution from element 1, and then you see the one in black color. These are the contribution to the force in the second element. Okay? And then the right hand side are the external force and some of the internal force. Okay, anyway, the internal force will be balanced out. But the external force are not 0 or not 2. You see? F2, M2, not 0. M3, 0. Okay? So, yeah. So even though you are taught about finite element, but in the end, you need to apply the right boundary value problem. Okay? So the correctness of the simulation depends very much on the boundary value. Okay? At one time, some of the senior complained, "Sir, why you have so many funny boundary conditions?" I have to tell you, in real life, there are more funny ones. Okay, some boundaries have to be replaced by statements. In the exam, the chain of boundary condition is already the easiest one. I don't test your solution for multiple variables, but you just use Cramer's rule, or you just solve 3 simultaneous equations to get the answer. Okay? Yeah, I don't do like other teachers or give you 4 or 5 variables to solve. Okay? They are mathematically complex, but physical too simple. Okay? So in this course, you are not just learning finite element. By solving the thing analytically, you got the symbolic expressions of the mechanics. Okay? Finite element simulation, to be honest, this day is not 50 years or 70 years back. Okay? You have no lack of computing power. But what you are lacking is a sense. Okay? An engineer without the right sense is a disaster. Okay? You heard about a story about AI? What's the famous AI disaster? You heard about that? I think those from France will know about it. You give the keys to Boeing. When Boeing 737 Max go to crash, okay, they blame the pilot. This pilot must be drunken. This pilot had a tendency of suicide. But in the end, 737 Max, they have a crash in South Asia, Lion Air, and even is it the Ethiopia airline? Okay, that was because of the bad design without notification of to the pilot. Pilot was thinking they are flying 737, which is a 50 years old airplane. Okay, if I want to pitch up, I pull. If I want to dive down, I dive. But because 737 Max has a modification different from 737. 737 is a 50 years old design. But Boeing had more powerful turbine mounted to this 737 Max. You know what happened when your turbine engine is more powerful? This is the wing, this is the engine. What happened when the engine becomes more powerful? You pitch up or pitch down? If your engine below the wing getting more powerful, what happened to the airplane? Pitch up. Have you ever fly the paper aeroplane? When it pitch up too much, what happened? It stop and come down. So Boeing are not going to change the design or structure. So they have a smart engineer say, "Oh, I have a tendency of pitching too high. Then I should rectify that. If I'm going to pitch up too much, the software will come down to interfere with the pilot. If you pitch up, then I'll pitch down by software. Okay? So too bad the two airplanes bought by the Lion Air and the Ethiopian Airline, okay, they have their angle of attack sensor getting defect. Okay, also too bad Boeing will don't have a redundant angle attack sensor. Okay, because these two companies are buying a cheap version, they may bring out another second redundant sensor. What happens? So when the pilot find that the airplane coming down, okay, they try to pull it up, and then the computer will then fight with the pilot to dive it down further. So that already appeared in the report. I think the pilot on the Lion Air, in the very last minute, is fighting with the computer. They will switch on the computer and then try to overpower the computer to bring the diving aircraft up. Okay, so yeah, that's to say, don't believe if you have a sense of directions, drive by yourself. Okay, so likewise for finite element simulation, I will also comment the same. Please don't believe in finite element if you have means to do the first analysis, okay, by hand. Okay, very often finite element simulations is only valid after you already do checking many times. Okay, people have a history of record what the simulation can go. Okay, they are only doing some minor modification. The first thing that finite element simulation will go wrong is if you don't have the right material property. Okay. For example, Boeing, why they shy away from using carbon fiber? Why the carbon fiber they are using is still 50 years old? Because material testing takes time. The data takes time. Okay? So if you don't have the validated material data and you don't do the simulation correctly, okay, your error can be quite severe, especially for carbon fiber composite. If you ever play with carbon fiber composite, you know that whoever who cure it will have different pre-stress and strength. Okay, it's almost curing of the carbon fiber is just the same way as different people who cook different cake with different taste, even though the ingredient is the same, because it's about the baking. Okay, baking of your flour, your butter, and egg. Okay. Different temperature will result in different crispiness or taste. Okay. So likewise, simulation, please be alerted. You need to do the validation. That's why we just now give you example to do the validation. Okay, next we come to the solution of this equation. See, this is a three equation with three unknown. Okay, how do you do the solution? Yeah, we practice Gaussian elimination again. The first thing we're going to zero out is 6L. How to zero out the 6L? Take the first equation and then minus 4 times the third equation. Okay? When 24 times L minus 4 times 6L. So you zero this out. Okay? And then, so this is the first zero. And then next, I want to zero out the minus 8L. I can zero out minus 8L by having the sum of the two. Okay? Okay? So I will get the sum of the second equation. Then the third row will have first two coefficients being 0. Then I can straight away solve for theta 3. Theta 3 is equal to minus 500L plus 5000L plus 2500 divided by minus 8L squared. So in this way I solve for theta 3. After you solve theta 3, do the substitution back into the second equation. Then because theta 3 is known, theta 2 can be solved. Okay? So this is quite an elaborate step. Can you please go back and practice it? Okay? Even though I didn't ask you to go back and study your advanced mathematics, okay? Then this will serve as a practice that you will do the recap. Okay, and then the last part. Okay, and then we come to the distributed loading. Back to the basic beam element in our formulation does not support any distributed load. Okay, this is a very pity that you have to handle in practice. Okay, but how do you get this distributed loaded to be lumped onto the node 1 and node 2? So we have the same way as we did before. We take about the work method. Okay, you know the work done by the distributed force. It's going to be the vertical displacement times the vertical distributed force. You do the integration there. That must be equal to the work done by the lump force. Okay, what's the lump force? Vertical displacement times vertical force on node 1 and node 2. Likewise, the moment times the angular displacement will present another work on node 2 and node 3, node 1 and node 2. Okay? So by writing these equivalence equations, okay, real work done by the vertical distributed force is equal to the lump force on each node, the work done by them, the lump force on node 1, and that force will be moment and vertical force. Okay? So, okay, let me write them down if you are not sure. So the way we do this method, we focus more on the derivation is to make sure that you understand the restriction. Okay? So when you go for your analysis, okay, they will ask you what kind of force you're going to apply. Normal force, surface force, or line force. Okay, if it's line force, then you are going to do something out with this now. Normal force is default. Okay? But the line force and the surface force is the equivalent version. Okay, look at the beam. When it's subjected to distributed loading, then it will bend. Okay. So how much work done by this? These diffractions at any position can be described by vertical displacement x. So the work done by Q can now be written as Qx v dx. Okay. To be more precise, Q times dx and then v. Okay. Because the v is also a function of x, so you have to bring them inside. And lastly, this program that is distributed force, we want to make it the equivalent lump force. Okay. So what are the displacement here? According to the convention, this is V1, this is V2, this is eta 2, this is eta 1. one force. Okay? How do you make this? Okay? To do so, it's very simple. If you want to find F1, you do the del F1 del V1. Okay, the rest of the term, all zero, is now going to be equal to, okay, equal to what? Equal to your del W, del V1. Okay, your expression here to be, okay, Qx, okay, del V, del V1. Okay, remember what your Vx? Your Vx is shape function 1, V1 plus shape function 2, beta 2 plus shape function 3, V2 plus shape function 4, beta 2. If the loading does not depend on the vertical displacement, only the vertical distributed displacement depending on the nodal displacement 1, then your del Vx, del V1 is going to be N1. Okay? So this expression can now be re-expressed as Qx N1 Vx. Okay? So that's the basis when you can find the equivalent nodal force. Okay? Okay, I should correct this here. I'm not differentiating the F1, I'm differentiating F1 del V1 del V1. So this is 1. Okay? So from the expression here, I obtain F1 is this expression. So that's the way how to find the equivalent force. Okay, so you see, W is equivalent, the work done by equivalent force, and is equal to the work done by the distributed force. Okay, so the displacement of the distributed, the displacement of the space is M1 V1 plus N2 beta 1 plus N3 V2 plus N4 beta 2. If you now do partial differentiation with respect to V1, then you got the force at Y1, okay? And then on the right hand side, you're only left with shape function 1 times Q0 dx. Okay? So in this way, you're able to find F1. So if you repeat the same, okay, you can find, okay, F11 is equal to Q0 L over 2. And then Fy2 is also equal to Q0 over 2. And the moment on the left hand side is Q0 L squared over 12. On the right hand side is Q0 L squared divided by epsilon times minus 1. Okay? So what did we do? When a beam is subjected to distributed load, okay, you can split up the vertical force onto two nodes, okay? But you don't split up the moment, okay? Your moment sum is 0 in the case of vertical forces, okay? Yeah. So that's the whole idea, okay? By graphing. Distributed loading, okay, a constant one called the bending upward, okay? Their effect is almost equal equivalent to 2 normal force upward of stage and 2 moment. And this 2 moment is, okay, what kind of moment? It is a moment that doing the popping up of the beam. So the one on the right hand side is negative, meaning it is clockwise. The one on the left hand side is counterclockwise. Okay? So in that way, you produce a equivalent deflection. Okay? So next, we see the example 4.6. Consider cantilever beam subjected to a uniform loading Q0, and its root is fixed such that V1 is 0 and theta is 0. Solve for the nodal displacement at the free pitch and the reaction at the group reaction. Okay? So in this case, you get your force balance for the beams, and then you set the first two degree of freedom to 0. And then because the loading case here is not the same, okay, then by substituting the equivalent loading on the right hand side, then you do the solution. Okay? Then you finally get the answer. Okay? So that's how you manage to solve it. Okay? Okay, for this part is already getting a bit involved. So please go back and practice yourself. I didn't go through it in detail very much, but pay attention to the physical meanings. What did you do? The mathematics there is just a tool. You need to know the physical meaning what you did. Okay? Just now I mentioned distributed loading. Okay? So it is curling up, yeah, or whichever. Then you do the calculation. Okay, next, we spend time on the frame structure. Okay, the idea of the frame structure is very close to what we had. Okay, a beam, how does it turn to a frame? Okay. Just now we talked about the beam along the line. Okay? But if you haven't that the beam is rotated by an angle with respect to the x-axis, as a result, the y-axis also rotates by an angle to phi. Okay? So this is the rotation. Okay, now in this case, what you really need to distinguish is, you need to distinguish the axial direction along the beam and also the vertical direction, also the transverse direction of the beam. Okay, you can see that the axial direction can be denoted by axis x prime, and the transverse direction can be denoted by coordinate y prime. Okay. So what's the displacement there? The displacement, and anyway, displacement don't change. Okay? So what you can do is, let's do the re-expressions. Okay. In the straight beam, you care about vertical displacement. Okay? In the inclined beam, as I'm not sure what is the direction, I can denote these to be U1, V1. But I still have to reduce the parts into axial direction and transverse direction. Okay? Anyway, the displacement sum must be the same. So what you do is, can you do the projections? Okay? What are projections? If I now draw this as a theta axis, the force, the displacement in the horizontal direction can be projected to be vertical component. If this is U1, this is U1 sine theta to be vertical to the axis. And if this one is the force, is the displacement in the vertical direction, I can project this into the vertical component V1 cosine theta. So as a result, what is the vertical displacement? It is V1 cosine phi minus U1 sine phi. Okay? Yeah, rather than using, we are not using theta, but phi as the angle. Okay. Likewise, how about the horizontal component? The horizontal component will have U1 cosine phi and then plus V1 sine phi. Okay. In this way, you got your this rotation matrix. U1 prime V1 prime is equal to rotation matrix times U1 V1. Okay. So this is the rotation. Then next, okay, what are we going to do next? Okay, now you can because in the case of beam element, you care only about the transverse displacement. The transverse displacement is V pi, the one vertical to the beam axis, the one vertical. Okay, but how about the angle of diffraction? The angle of diffraction does not change when you are changing in coordinate. Look at this bending. Does it change when I turn my head left or right? It doesn't change. But the vertical displacement, yes. Okay? So means the rotation of the coordinate, okay, doesn't change the rotational angle. Let's look at this beam, simple cantilever beam that bend under the wing. Okay, does not change in. Okay, look at the pitch here. Can you guys tell me what is the angle of diffraction? When you are saying angle of diffraction, I'm referring to the starting angle and the final angle. Okay, so it doesn't change. Okay, but gravity method. Okay, even though I said it doesn't change, we can change the coordinate. But gravity, because it remains vertical, so it does change. Okay, so in this case, in the absence of gravity, your coordinate change doesn't change the angle of diffraction. So as a result, by using the formula above, I can rewrite my expression. Okay, my transverse displacement and angle of diffraction, okay, can now be re-expressed as horizontal displacement, vertical displacement in the global coordinate, and the angle of diffraction. Okay, so this first part, okay, is related to the first note. The second part, okay, is related to the second note. So the best angle of rotation, you write them in the separate row and separate columns. Okay, so your transformation matrix is now expressed as this. And since you have written the transformation matrix, okay, you can now rewrite the global stiffness. In this case, the beam bending, the force balance for the beam are just the transverse force and moment at each point. But now since you want to do in terms of global coordinate, your angle v1 prime theta 1 prime v2 prime theta 2 prime can now be re-expressed in terms of global displacement v1 v1 theta 1 and global displacement v2 v2 theta 2. Okay, and through these operations, you can now combine the two metrics. This is 4x4 matrix. This is 4x6 matrix. After the multiplications of the two matrices, then you're going to have 4x6 matrix. Okay? And then next, you want to re-express the force. Okay? You might know vertical force and horizontal force. But when you want to apply these forces to the beam, the most important thing is to find out the transverse forces. The transverse forces is the force perpendicular to the beam. Okay? So what do you do next? Okay, you just convert these global forces into the x and y direction, or you have these transverse forces converted into x and y forces. Okay? So what do you do next? So you see here, because your global force Fx is just the projection of the transverse force into the y direction and x direction. Okay? So your transverse force is the force applied on the beam. It can be projected into Fx and Fy. Okay? So then you're going to have force projection on Node 1, Node 2. So as a result, this is going to be the re-expression of force. You see, the force projection on the Node 1 going to have a component x and component y. You have this minus sine phi f1 prime and then cosine phi f1 then 1 and 1. So this is a rotation matrix. Okay. So if you're not sure how to write it, then you can copy it down and give you a sense how to do the writing. So imagine now you have a beam. Your transverse force is F1. So this is the angle. This is also the angle phi. Then you can reduce your force into two components. What kind of component you want to do? You're going to do sine phi. Okay. So you see here? So your F1 x. Okay. But because of the direction is pointed backward, so this is negative. Okay. F1 minus sine phi F1 1 prime. Second, F1y, okay, it is still upward, cosine phi F1 y prime. Okay? Does the moment change? No, moment doesn't change. So moment on the left node, angle don't change. Moment on that angle will change. So it is N1 1 and 1 prime. Okay? So likewise for the second node, you do the same. Okay, minus sine F2y prime is equal to F2x. And then cosine phi F2y prime is equal to F2y. And the moment on the second node, F2 don't change. It's equal to F2 prime. After you know this, what do you do next? Okay? You know the right expression is the local force for the beam. Vertical force on the beam, moment on the beam. Okay? If you now multiply this local force on the beam with the rotation matrix transpose, then you're going to have a global forces. Force in the x direction, force in the y direction, and even the moment of each node by doing this multiplication. Okay? So as a result, your this 2D beam element we're going to have global forces is equal to rotational matrix transpose 6 times 4 matrix times 4 by 4 matrix times 4 by 6 matrix times the displacement vector of 6 by 1. So these operations will give you these complex expressions. Okay? Since you are given this MATLAB symbolic, if you want to practice it, you can go and try them out. It's quite a tedious process, but since you have that, then you can feel free to do that. So after you have all done the beam stiffness and beam forces, okay, what's next? The next part of interest is you can combine the beam with a truss to make a frame. Okay? So what's good use for that? Okay, now you see, because you have a truss and you have a beam, they contribute to different coordinate. Truss only contribute to horizontal displacement. Beam only contribute to vertical displacement. So they don't meet each other. Okay? You're basically having the forces in the x direction plus forces in the y direction. So what you see here, they appear in different rows and different columns. They don't couple. Okay? So it's quite easy to write this. Okay? But for solution, if you know it right, you can do divide and conquer. Okay? So 1D frame and 1D truss is simple in appearance. So it is just 1, 2, 3, 4, 5, 6. 6 by 6 matrix and 6 by 1 displacement vector. In this case, your 6 by 1 displacement vector has horizontal displacement at node 1, vertical displacement at node 2, and then angular displacement in node 1. And then the same for the second node. Second node have horizontal, vertical, and angular displacements. Okay? Okay, the complex thing comes for 2D. 2D, you learn about the 2D truss. Okay, 2D truss, it is basically a stiffness times the expression resulted from the rotation. And then, likewise, for the beam bending, supposedly so this one you can do the three expressions, okay, for the truss element. Okay, but I wouldn't suggest you to do that. Just stick to the original. Any simplification, you do it later. before that we already derived. It could be a 2D beam element expressed in terms of U1, U1, theta 1, U2, B2, theta 2. So you can see that truss element in 2D will be coupled with the horizontal vertical displacement for a beam, okay? But it is independent of the angle, okay? So in this case, let's see the two. Okay, by doing the sum, you can have these complex expressions, okay? Yeah, I won't go through with solving this, but please know that you can do the divide and conquer for certain solution, okay? And then next we come to the example of the bracket. Okay, in reality, yeah, we wouldn't always handle one beam and one column. Okay? Yeah, but this is one of the simplest example that you can solve. Since you are given the cantilever on the support of the column, will you be able to find the free node displacement on node B? Okay? So this is easy to solve, but you still have three unknown variables to solve because the point C is clamped, point O is clamped, so only free N is point B. So what you have to do is, okay, because it's all horizontal, it's quite simple to solve. So the horizontal beam and horizontal truss is easy, vertical beam and vertical truss is easy. Then, but you got to express the K for trusses in terms of EA over L, but structural rigidity of the beam is going to be expressed as EI over L. Then you can find out, okay, what would be the equation for the horizontal beam or horizontal frame. So because one end is fixed, the other end is free, then you can only take care of the free end on the node 2. And then for the vertical chord pillar, you only care about the node 2 as well. Then this is your inner matrix. You combine the two together. Okay? You combine the two together. Then you have this force matrix. Okay? And then next, apply the vertical loading. Then you should be able to find the solution. Okay? Yeah, so all these are quite tedious, but I think with simple practice, you should be able to do that. Yeah. So in the end, after all the handling, you only have these three simultaneous equations. Okay. So yeah, I think the only way of learning this is by practice. There are no second way. Okay. Everything is given to you. Please go back and read up and try it on. Even the MATLAB or coding calculation is there. But I would still suggest you to do hand calculation. MATLAB one is good for handling PDST, but you have to go through the first round. Okay? After the Gaussian elimination, you will be able to solve this. Okay? Yeah, you might ask, why do I bother this much? Okay? Later I will show you some examples. Okay? For this part, the portion I will leave it for next time. Okay, next week I think you can practice your beam element. Okay, at the same time I will post the exercise for the beam. Okay, yeah. So this should be sufficient. And not to forget about this ANSYS hands-on. I asked you, how could you find the rigidity of the drinking straw? Have you figured out how do you calculate the Young modulus of your drinking straw? Have you tried experiment with the drinking straw? How to find the bending? How to find the rigidity? EI. Look at the example from today. Okay. distributed force in the experiment. Difficult. Okay. Are you able to apply point force? Yes. Since you are able to apply point force, look at this example. Okay? You can apply the force at the middle and then find the diffraction. Then you go back to find out the modulus. Okay? So that's why I'm not in a hurry to ask you to present the first one. I'll let you have some understanding of the beam. Can you go back and find out what is the fractional rigidity? Okay. This one don't need ANSYS calculation. Don't need ANSYS derivation. Can you go back and do hand calculations? How do you support the drinking straw? And then load it at the middle. And then form the diffraction. Please go back and calculate what is the rigidity. Okay, of course, this one is different from your this drinking straw. Your drinking straw is a tube, but this one is a solid piece. So your eye will be different. Yeah. But yeah, in a way you could use it. So any question for your this ANSYS and so on? The 3D space truss. Yeah. Okay. Yeah. If not, then please go back and try. I think next week we try to arrange it to be ANSYS session again for beam. But at the same time, you can do the analysis of your these drinking straws. Okay, so that you get your formula, get your vector quantity, the formula. Okay, with this, then we are done.